Hello everyone. Today is our seventh live session of the course Semiconductor Devices and Circuits. Course is being taught by Professor Sanjeev Sambhadan, and we have been solving the problems in the live session since last 6 weeks. And today we will start by solving the problems regarding the PN junctions. Okay. So as many of you, I shouldn't say many, as some of you had posted or emailed me regarding the solutions of the assignment problems. So in the previous case, I'm talking about the metal semiconductor junction. I solved those problems which were asked over email, and in today's session I have also received two or three problems which I have been told to solve, and we will see those problems. So you are welcome to check the recording if you are not able to join currently. So the all the problems that were asked over email, I guess it was yesterday or day before yesterday, I guess. So all the problems that had been asked, I have included them and we will be solving them. So once again, I would like to add that you are welcome to ask questions by sending me an email, or and my email address is this. Okay. So let's begin by saying, okay, in previous assignment, uh, there was one problem about this metal semiconductor junction where we had been told to find which of the statement was incorrect. Okay, so uh, the if we look at the options, it says that thermionic emission depends on the shape of the band bending inside the semiconductor. And as I said, for example, let me draw a rough metal semiconductor interface. Okay, and as we said, this is the thermionic emission part and this was the tunneling part. Although there will be this, what we can say, the recombination and diffusion parts as well, but let's not go into those. Okay, which will be associated with the electrons and holes. Let me draw the let me say this is the thermionic emission part and this is the tunneling part. Okay, let me turn off the video for the bandwidth preservation. So this is the tunneling part, and we said the thermionic emission is the over the barrier transport. Okay, it has to go, or it has to cross this barrier. The carriers have to cross this barrier in order to go from one side to another side. So clearly it does not depend on the band bending, it will depend on the this barrier height. So option A will be the incorrect option, so we will select this option. But also let's look into the other options as well. So it says that tunneling current through a triangular barrier at the junction increases with the doping concentration in the semiconductor, and it's true. Okay, as the doping increases, this barrier narrows down and we will be having enhancement in tunneling. Okay, that's what we had seen previously. And also, talking about the diffusion transport through this junction, it will be negligible under the reverse bias, which is also true. So this statement is true, this statement is also true, and it says that thermionic emission enhances with the temperature. Okay, with the increased temperature. It is also true because now more carriers, more carriers, sorry, can cross or move over the barrier because of high higher thermal energy. Okay, so this statement is also true. Okay, so only the first statement is incorrect, so we will select that particular statement only. Okay, now let's move to another problem. It says that we have this one-sided p-n junction, and this on the p side it is highly doped. That's why on p side we have p side is highly doped. Okay, is highly doped. So depletion width will be less on p side as compared to n side. Okay, so as you can see, we have this one-sided p-n junction charge profile, and it is given below. And for this p-n junction, the graph of the capacitance, the junction capacitance versus the bias is shown for the uh, where this VR will be the reverse bias, and we have been told to find the value of the donor concentrations. Okay, that is the doping on the n side. We have been given this graph, this 1 by Cj square versus the reverse bias. Okay, or the and we have been told that the relative permittivity of silicon is 11.7, and the slope of this line, which is this line, this straight line, is 6.15 into 10 to the power of 15 farad per centimeter square raised power minus 2 volt inverse. Okay, so what we have been given is the depletion width. Okay, we can reduce the depletion width from this expression, which is xd, which is simply 2 times, you must have done it in the lectures taught by the professor, where VBI is the built-in potential and VR is the reverse bias, by Q 1 by NA plus 1 by ND. Okay, this is the depletion width. Okay, let me write it down. Depletion width for reverse biased p-n junction. Okay, so now, as we have seen in this case, since it is the highly doped p side, since it is p plus n junction, what we will be having is, the acceptor doping will be much greater than the donor doping. So we can write this depletion width to be approximately equal to 2 times epsilon naught epsilon r VBI plus the bias divided by Q, and this simply means this is NA plus ND divided by NA and D, and this, since this NA is much greater than ND, we can say Na plus Nd is approximately Na. Okay, so the expression 1, let me denote it by 1, reduces to Wd 2 times epsilon naught epsilon r Vbi plus Vr by Q. This whole thing will now be divided by simply Nd, because this is Na divided by Na Nd, this whole thing. Okay, so the Na and Na will go and we will be left with this Nd thing only. Okay, now let us find this junction capacitance per unit area. Okay, let's find this junction capacitance per unit area, and it will be simply, if now this, let us note it by Cj, which is given in the problem. It is simply Cj is the junction capacitance and is given by epsilon naught epsilon r by Wd. This is the junction capacitance per unit area. That's what we require. Okay, so Cj is now simply epsilon naught epsilon r by Wd. W is simply 2 times epsilon naught epsilon r Vbi plus Vr square root into Q and T. This will be also under square. Okay, or simply this Cj is equal to epsilon naught epsilon r Q times Nd by 2 times Vbi plus Vr. This whole thing will be under square root. Now squaring both sides, we get Cj square to be equal to epsilon naught epsilon r Q times Nd 2 times Vbi plus Vr, or simply 1 by Cj square is 2 times Vbi plus Vr divided by epsilon naught epsilon r Q times Nd. Okay, so we have got this. We have got this expression for the 1 by Cj square, and it is a linear function of the reverse bias. Okay, it is a linear function of the reverse bias, linear with respect to the Vr. Okay, now if we look into the figure, we see that this point, at this point 1 by Cj square is equal to 0. Okay, so 1 by Cj square is equal to 0. 1 by Cj square equal to 0. Let's put this equal to 0. So it implies Vbi is equal to minus Vr. Okay, and from figure Vr is minus 0.725, thus Vbi is 0.725 volts. Okay, so this is the value of this built-in potential. Now we have also been given the slope. The slope is equal to 6.15 into 10 to the power of 15 times the farad per centimeter square minus 2 volt inverse. Okay, This is the slope. And also from this equation, slope is equal to 2 by epsilon naught epsilon r q and d. 2 by q times epsilon naught epsilon r times nd. So it implies nd, which is the donor doping concentration, is simply equal to 2 times q times epsilon naught epsilon r times the slope. Okay, so nd is equal to 2 divided by 1.6 into 10 to the power of minus 19. Epsilon naught is simply 8.85 into 10 to the power of minus 14, and epsilon r is 11.7 times the slope value, which is 6.15 into 10 to the power of 15. Okay, let's solve this. Let's solve for this. So it is 1.6 times 8.85 times 11.7 times 6.15. So it's coming out to be equal to 2 divided by 1.108 into 10 to the power of 50, or simply 2 divided by 1.018, which is 1.96. So nd is equal to 1.96 into 10 to the power of 15 per centimeter. So we have been able to find the doping concentration. Okay, let me write it again. So we have been able to find the doping concentration from the plot of the capacitance versus the bias. Okay, first of all, we found out the value for the VBI, as it was given from in the figure, that at this point, which is denoted in black over here, the Cj 1 by Cj square is equal to 0. So let's move to the other part of this problem, which says that in question 1, which is the same problem, what is the concentration of the acceptor atoms? Okay, previously we said that the doping concentration of acceptor atoms is much greater than the doping concentration of the donor atoms. That's how we were able to approximate this depletion width in terms of the donor impurities only. Okay, and we should verify this as well. Okay, when we solve for this Na. Okay, now for this Na, we know that this built-in potential is simply Kt by Q, 1 of Na Nd by Ni square. Okay, so it is well known. When we studied the p-n junction, this relation was established, okay, by the professor. So now if we take ln on both sides, what we will get? We will get ln of VBI by Kt over Q is equal to Na Nd by Ni squared. Okay, so if I now substitute the values, 1 of VBI we found out previously, and it was equal to 0.725. Okay, so it is equal to 0.725, and Kt over Q is the thermal voltage at room temperature, and it is equal to 0.026 volts. Ni square is Ni is 10 to the power of 10, so Ni square is 10 to the power uh, 10 to the power 10 whole squared, divided by Nd is Na, and Nd we found out in the previous problem, it was 1.96 into 10 to the power of 15, so it is 1.96 into 10 to the power of 50. Okay, so let's solve for this. It is ln of 0.725 divided by 0.026, which is 3.32, times this whole thing, so okay, what we have done, there is a mistake over. Okay, so I have taking exponential on both sides. Okay, that's why I was wondering why is this value coming out to be so small. I have to take exponential on both sides. Okay, so if I take the exponential on both sides, then this ln will go. Okay, then only this ln will go, and we will be having exponential of VBI by KT over Q. Okay, so this will be exponential. So otherwise it would have come a minuscule number, and the approximation that we had used would not have been the correct one. So the mathematical error which we did helped us to gain insights, further insights. How we were able to get insights is quite simple. We had said that we had looked into this picture at first. Okay, and when we saw this picture, we said that N side is highly low doped as compared to the P side. Okay, this is a P plus N junction, so the acceptor impurity is much greater than the donor. So as a result of this thing, Na is much greater than Nd. So when we did this error, when I did this error, okay, I didn't take the exponential. When I had to take the exponential on the left side, and I missed out. I said it's ln. Okay, so when I solved for the problem, I didn't get the number which I was looking for. So when I solved it using this now correct methodology, which is that I had to take the exponential on both sides, but by mistake I wrote ln on both sides. Okay, so now this Na is simply this 10 to the power of 20 times this is exponential of 27.88. Okay, divided by this 1.96 into 10 to the power of 15. So the value of Na comes out to be equal to 1.64 into 10 to the power of 17 centimeter cube. So our assumption that we used in this relation, that Na is much greater than Nd, is valid. Okay, because this is of the order of 10 to the power of 17, and Na is of the order of 10 to the power of, sorry, Nd was of the order of 10 to the power 15, and Na is of the order of 10 to the power of 17. So it is quite 2 orders of magnitude difference. So it is quite huge. Okay, now moving to another problem which is associated with this diode model. Okay, so we have to consider a circuit given in this figure. Okay, the diode is forward biased. Okay, this DC voltage is used to forward bias the diodes. Okay, so it is used to forward bias this diode. Okay, we have to forward bias this diode, and there will be some DC current flowing through this circuitry at this thermal voltage, that is room temperature, and at room temperature it is approximately equal to 26 millivolts. So the junction capacitance of this PN junction diode at operating point is 1 nanofarad. So we have been given the value of this junction capacitance and also the frequency at which we are operating. Now we have to find the magnitude of the small signal current which is flowing through this diode, which is in microamperes. Okay, the current will be in microamperes. So let us first draw or replace this diode. This diode will simply be, it will simply be replaced with a resistor and a capacitor. Okay, this will be some resistance RD and this will be some junction capacitance minus J times X. Okay, now when we look into this RD, this RD is the resistance of diode, that is the specific AC resistance of diode, and it is simply given by Vt by Id, and Vt is 26 millivolts and Id is simply, Id is this DC current which is 13 microamperes. Okay, so it is 13 microamperes. So it will be simply 2 kilo ohms. Okay, micro is 10 to the power of minus 6 and milli is 10 to the power of minus 3. So it will be 2 kilo ohms. Now if I draw the complete circuit, considering that the diode is forward bias, now we will be having this AC source considering this small signal model, and this has the magnitude of 5 sine omega t millivolts, and this will be our diode model which is 2 kilo ohms is this RD, and this is our junction capacitance in parallel with this resistance, and we have a load, of 100 ohm. Okay, we have a load of 100 ohm. Okay, so it is 100 ohm. Okay, now this AC resistance, sorry, AC current will simply, its magnitude will simply given by this AC voltage divided by the total resistance or the total impedance we are having, which is Z1 plus Z2. So if this whole thing is Z1 and if this is Z2, they are in series. So this will be the total magnitude of the AC current flow. So now this Z1 is simply the parallel combination of this capacitance and the RD resistance, which is 2 kilo ohms, and it simply means this XC is equal to 1 by omega C, where omega is the operating frequency and it is equal to 10 to the power of 6 radians. Okay, so it is simply 10 to the power of 6 radians, and C is the this capacitance, this junction capacitance, and it is 1 nanofarad. So it is 10 to the power of minus 9, or simply omega C is 10 to the power of 3. So Z1 is simply minus J times 10 to the power of 3. Okay, sorry, this J times XC. Okay, let's be clear. Okay, minus J times XC is this value. Okay, so now let's solve for this Z1. Since a parallel combination, it will simply be this Z1, sorry, wait a second. I don't know what is happening with this thing. Okay, something crashed. So this Z1 is simply it is simply this parallel combination, which will be minus j times 10 to the power of 3 into 2 kilo ohm is the RD, 2 into 10 to the power of 3 divided by, if I take 10 to the power 3 common, it will be 2 minus j. So let's cancel this out, this 10 to the power of 3, and we will simply get the Z1 to be equal to this thing, which is minus 2 into 10 to the power of 3 times j divided by 2 minus j, and Z1 plus Z2, which is the total impedance, is simply equal to minus 2 into 10 to the power of 3 j 2 minus j plus Z2. Z2 is simply zero point 0.1 kilo ohm into 10 to the power of 3. So it is simply minus 2 into 10 to the power of 3 j plus 0.2 into 10 to the power of 3 minus 0.2 into 10 to the power of 3j. So it is divided by 2 minus j. It is simply zero point 0.2 into 10 to the power of 3 minus 2.1 j into 10 to the power of 3, okay, divided by 2 minus j. So the magnitude of this whole thing will simply be equal to this mod of z1 plus z2 is simply equal to 10 to the power of 3, let's take it common, square root zero point 0.2 whole square plus 2.1 whole square divided by 2 square plus 1 square. So let's solve for this. It is 10 to the power of 3 root of 0.04 plus 4.41 divided by root of 5. So it is simply 0.943 into 10 to the power of 3 ohm, and IAC is simply this AC voltage is 5 millivolts, okay, 5 millivolts, 5 sine omega t. So it is simply 5 into 10 to the power of minus 3 divided by 0.943 into 10 to the power of 3, or simply it is equal to 5.3 into 10 to the power of minus 6 amperes, or it is equal to 5.3 microamperes. Okay, so option A is the correct option to go with. Okay, now moving to another problem, which is also associated with the junction formation, and in this case we are having the donor impurity on the both sides, and on the one side we are having the concentration of 10 to the power of 16, and on the other side we are having the concentration of 10 to the power of 15. So we have been told to find the value of this built-in voltage. So on left side, if I draw the EC, let's say this is our EC, this is our EF, and this is our EV. and on the right hand side it is a bit farther away. Okay, the Fermi is bit farther away. Rest everything is same. Okay, so if I now bring these two materials together by connecting them with a wire, let's say, so there will be the equilibration, and now we will be having a constant Fermi level throughout. Okay, so this will be the constant Fermi level and it will remain close to the conduction band edge on the left side, and it will be a bit far from the conduction band edge on the right hand side, because it had we had previously seen that this side has less concentration. Okay, less Nd concentration. So if this is our interface, then this is what it looks like. Okay, this will be the band bending, this will be the EI, and this will be the EV. Okay, now this will be our built-in potential. Okay, which is simply Q phi pi. Okay, and this is our band bending that we have got, and this is x equal to 0, that's at the junction. Okay, so we can clearly see this Q phi pi is simply EC2 minus EC1. Okay, and we also know at thermal equilibrium the majority carrier concentration is simply Nd1 equal to, which let us say it's on the left hand side, is simply Nc, which is the effective density of states. Since it is the same material, so the effective density of states will be same, exponential of Ef minus Ec1 by Kt, and it will be Nd2 Nc times exponential of Ef minus Ec2 over Kt. Okay, so we have got the concentrations on the N side, which is having high doping, and on the other N side which is having less doping. So we can simply say, if we divide this Nd1, dividing both, what we will get Nd1 by Nd2 to be equal to simply Nc times exponential of Ef minus Ec1 by Kt divided by Nc times exponential of Ef minus Ec2 over Kt. Okay, so since this is the same material, so this Nc and Nc will go, and we will be left with exponential of EC2 minus EC1 over KT. So this ND1 by ND2. Now what we can do, we will take 1 on both sides. Okay, so it will be simply KT times ln of ND1 by ND2 is equal to EC2 minus EC1, and this EC2 minus EC1 is simply Q phi bi. Okay, it is simply, now this will be simply KT by Q ln of ND1 by ND2 by equal to phi bi. Okay, so this phi bi is KT over Q, it is 26 millivolts ln of ND1 is 10 to the power of 16, it is 10 to the power of 16, and it is 10 to the power of 15, so it is simply ln of 10. Okay, or this phi bi will come out to be equal to 26 into ln of 10 is simply, okay, it is 60 millivolts. So option A is the correct option to go with. Okay, now moving to another problem which is quite good to solve. Okay, it says that, let's look into the problem first, let's zoom into this. So it says that a charge profile of a p-n junction with the intrinsic region in between is given such that the p-n junction is n-type, okay, for minus x between minus w to minus 0.5, and it's intrinsic for the region between minus 0.5 to plus 0.5, and it is p-type for the region between 0.5 to w. Okay, so we are having this as our intrinsic region, this will be our intrinsic region. Okay, so the concentration of Na and Nd are both equal, and we have to find the value of this built-in voltage. Okay, so on the right hand side we have this p side, and in middle we have this intrinsic region, and on the left hand side we have this N. So let's draw the energy band diagram first, with EF being constant throughout. Okay, so on left hand side what we will be having, we will be having this EC of N, that is the conduction band on the N side. Similarly, we will be having this EV of P, which is the valence band on the P side. So we have drawn both the valence band edge and the conduction band, edge on the N and P sides. Okay, so it's on the N side and it is on the ECP. Now we are having this intrinsic region. Okay, this will be our intrinsic region. In this region we will be having this band bending, but since there is no charge inside this region, okay, the charge lies outside. As a result, if we use the Gauss law, okay, del dot E is rho by epsilon, so we have to use the Gauss law, and from the Gauss law we can deduce that the electric field will be straight line in this region. Okay, because del dot E, del dot some constant, this constant is equal to 0. Okay, that's why there will be no charge in this. Okay, so this will be our band bending, with this being the straight line. Okay, and in total we will be having this as our intrinsic region, and this is minus W, this will be plus W, this will be minus 0.5, this will be plus 0.5. Okay, and this is our intrinsic region. Intrinsic region. And in total we are having this much amount of built-in potential in this device. Okay, this is the built-in potential. So this intrinsic region has enhanced this region. Okay, so we can simply say this Q phi bi is simply ECP minus ECN, just using energy balance. Okay, so we have used energy balance and we have got this expression. Okay, so this and D, which is the donor doping concentration, is simply equal to NC times exponential of EF minus ECN by KT. Okay, and similarly on P side, this N naught of 2 is simply equal to the intrinsic carrier concentration by the acceptor impurity, and it will simply be NC exponential of EF minus ECP by KT. Okay, so if we divide this equation, dividing 1 and 2, we get simply Na Nd by Ni squared is simply exponential of ECP minus ECN by KT. So if we take ln on both sides, it will be simply KT times ln of Na Nd by Ni square is ECP minus ECN, or this ECP minus ECN is simply Q times phi bi KT ln of Na Nd by Ni square, or this phi bi is simply KT by Q ln of Na Nd by Ni square. KT over Q is simply 26 millivolts ln of Na and Nd are both 10 to the power of 15. Okay, they are both 10 to the power of 15. So it will be 10 to the power of 15 into 10 to the power of 15 by Ni square, which is 10 to the power of 10 whole square. It is 26 millivolts times ln of 10 to the power of 10. It is simply 0.6 volts. So this is the value of the phi bi, what we got in this problem. Now we have been told to find the 2 times W. What is the value of this 2 times W? Okay, so we have to find out in the same question, we have to find out the value of this 2 times W, and this W was simply the depletion widths on the N and the P sides. Okay, so since the doping was same on the both sides, that's why on both sides we had the same depletion widths. Okay, since the doping is of the order of 10 to the power of 15 per centimeter cube, and as a result of this thing, sorry, we will be having, if I draw the electric field versus the position, if this is my electric field, with position in the intrinsic region, which is between minus 0.5 to plus 0.5, we are having the constant electric field. Okay, because there is no net charge inside this region. Okay, and we are having this as the depletion width on the one side, and this as the depletion width on the P side. Okay, so this is the maximum field value. Okay, and this is our intrinsic region. So this is our intrinsic region. So we know that if we integrate this electric field with a position, we will get the potential, which is the built-in potential. So the area under this whole function, so the area under electric field, sorry, I don't know what has happened with this thing, sorry again. Sorry. So the area, let's again write this thing, under electric field gives built-in voltage. Okay, so the built-in voltage or built-in potential is simply equal to, if I look for this region first, it would be simply, this is 0.5 times the Emax. Okay, Emax, let me use curly E for this, Emax times 0.5 plus, for this thing we are having the area of the triangle, which is 1/2 of base into altitude. Base will be W minus 0.5 times the Emax, and this has to be multiplied with 2 because we have to consider this area as well. Okay, so this will be the total area. Okay, so it will be simply 2 times this thing is Emax times this is 0.5 plus W. So let's name this as equation 1, and also if we use the Poisson's equation, we can write this electric field to be simply equal to Q times Na W minus X by epsilon naught epsilon R. Okay, so this electric field maximum, let's say let us take electric field value at x equal to 0.5 micrometers. So they at this x equal to 0.5 micrometer, E is having the value of E max. Okay, it is still having the value of E max, and E is, the field is still E max. Okay, so the E max is simply equal to Q times Na using this equation. Let's say this is A. Okay, using A we get Na W minus 0.5 by epsilon naught epsilon. Let's name this as equation 2, and let's use both the equations, that is equation 1 and equation 2. What we will get is we will simply substitute value of Emax in equation 1. So it will simply be equal to, this phi bi will simply be equal to Q times Na by epsilon naught epsilon R W minus 0.5 times W plus 0.5. So it is simply phi bi times epsilon naught epsilon R by Q Na equal to W square minus 0.5 whole square. So we are talking everything in meters over here. Okay, so we are talking in meters, everything is in meters. Let's be careful about the units now, because it can create problems for us. Okay, so phi bi we found out in previous problem, it is 0.6. So it is 0.6 times 8.85 into 10 to the power of minus 14. So I have used units of centimeter. Okay, so let's be careful. Into 10 to 11.7 divided by Q is 1.6 into 10 to the power of minus 19, and Na is having the value of 10 to the power of 15 per centimeter cube. So it will be W square minus, so since it is in meters, 10 to the power of minus 12 meters, so it is simply 25 meters square. So let me write it like this is in centimeter square, and this will be simply 0.25 micrometer square, which will be 25 into 10 to the power of minus 14 meter square. Okay, so it will be simply now this, if I multiply this whole thing, it would be simply equal to 38.83 into 10 to the power of minus 14 meter square plus 25 into 10 to the power of minus 14 meter square is W square. So it is simply root of this thing 63.83 times 10 to the power of minus 7 meter is the W value. Now taking the square root of this thing, it is simply 7.98 into 10 to the power of minus 7 meter is W, or W is 0.798 micrometer, or 2W is simply 1.596 micrometers. Okay, so let's move to the other problem, which says that we have to find out the electric field at x equal to 0. So the electric field at x equal to 0. So electric field is simply, it came out to be equal to phi bi equal to this expression E max plus 0.5 plus W. Okay, is simply E max plus W. This is micrometer. Okay, so it is simply phi bi is 0.6 E max times 0.5 plus W came out to be equal to 0.798. 0.798 micrometer. So it is simply 0.6 divided by 1.298 into 10 to the power of 6 volt per meter is the Emax, or Emax is simply 4.62 into 10 to the power of 5 volt per meter. So option C is the correct option to go with. Okay, now moving to another problem, which says that we have this abrupt junction. Okay, we have an abrupt PN junction at T equal to 300 Kelvin, and it is uniformly doped with acceptor of concentration of 10 to the power of 18 and the donor concentration of 10 to the power of 15, and the PN junction area has been given to us, which is 6 into 10 to the power of 4 centimeter square, and we have also placed an inductance in parallel with this PN junction. We know that this PN junction, when in a reverse bias, it will be having some junction capacitance associated with this, and this junction capacitance will be, since this reverse bias, we will be having this junction capacitance, and in this, and with this junction capacitance in parallel with this some inductor which we are placing in parallel, we will be having this LC kind of a circuit. Okay, so this LC circuit will have now some frequency associated with it. Okay, so we have been told to find that resonant frequency of this LC tank circuit. Okay, because we know that this PN junction will be acting as a capacitor in the reverse bias, and reverse bias voltage is given to be equal to 1 volt. This has also been said to us. So this abrupt PN junction is uniformly doped. So let us say simply this will the capacitor the capacitor will be in parallel with the inductor. So we will be having the resonant frequency of LC circuit simply equal to, if this is the f naught is the resonant frequency, it will be simply given by 1 by 2 pi 1 by 2 pi root over LC. Okay, 1 by 2 pi root over LC. So it is simply, we have to find this value of the capacitance, which will be simply epsilon naught epsilon r, this time it's not per unit area, divided by WD, where WD is the depletion. Now this WD is simply given by 2 times epsilon naught epsilon r VBI plus VR by Q 1 by NA plus 1 by ND square. So from this, for this expression, first we need to find the VBI. VBI is simply KT over Q ln of NA ND by NI square. So it is simply 0.026 ln of NA. NA is 10 to the power of 18 and ND is 10 to the power of 15 divided by Ni square. Ni is 1.5 into 10 to the power of 10 whole square. So VBI will be, this value will be simply equal to 0.76 volts, and from this VBI we can find now WD. WD can be found out by putting the values, it will simply be equal to 2 times 8.85 into 10 to the power of minus 14 into 11.7 times this VBI plus VR. VR is the reverse bias voltage, which is 1 volt minus 1, so it is plus, divided by Q 1.6 10 to the power of minus 19 times Na plus Nd divided by NaNd, it will be 10 to the power of 18 plus 10 to the power of 15 divided by 10 to the power of 18 into 10 to the power of 15. So we will get some value of WD, put it in this equation 1, put it in equation 1, and we get C. From that we get the value of F naught. Okay, so that's what, since this is quite tedious calculation, it is just mathematical thing that we need to continuously do, so we have skipped this thing, and we will be able to get the value of this resonant frequency at which we are going to get when we are going to place this inductor in parallel with the PN junction. Okay. Now moving to another problem which is also associated with this ideal PN junction, says that the current through an ideal PN junction diode at 300 Kelvin is 2 milliamperes when a forward bias of 0.1 volt is applied. So we have been told to find the reverse saturation current. So the expression for the current is simply I times I naught exponential of VA by VTH minus 1. Okay. So I naught, so I is 2 milliamperes. So it's 2 times exponential of VA is 0.1, VTH is 0.026 minus 1. So it is simply I naught times exponential of 3.85 minus 1, or it is simply 2 divided by 45.99. It is milliamperes. Okay. I naught, or I naught, which is the reverse saturation current, is simply 43.7 microamps. So option A is the correct option to go with, and we can say that we can clearly see from this that the reverse saturation current, there is quite number of orders magnitude difference between the forward current and the reverse saturation current, even at the uh, 0.1 volt of forward bias. Moving to another problem which is also associated with this ideal PN junction, and this is forward biased moderately such that the applied bias is much greater than the thermal voltage. Okay. So if VA is the applied bias, it is much greater than the thermal voltage. Okay. So it is much greater than the thermal voltage. So we have been told to find out how much voltage is needed to increase the diode current by a factor of 10 at 300 Kelvin. So it is at 300 Kelvin. Okay. So since VA is much greater than VTH, we can write this simply ignoring the factor of minus 1, which we can simply write VA by VTH. Okay. Now if we have to find the voltage that is needed to increase the diode current by a factor of 10, so let me write down that delta VA is additional voltage required to increase the current by 10 times. So the new current is 10 times I is I naught times exponential of VA plus delta V by VTH. Okay, it is simply I naught times exponential of VA by VTH times exponential of delta VA by VTH. This whole thing is equal to I. is equal to I. Okay, so 10 times I is simply I times exponential of delta VA by VTH. So I and I will go, and we will be left with VTH times 1 of 10 is equal to delta VA, or simply delta VA is equal to 60 millivolts. So delta VA is option B is the correct option to go with. So let's recap all the problems that were associated with the PN junction and one problem that was associated with the metal semiconductor junction. In that problem, what we said was that they basically we mainly concentrated on the two transport mechanisms, which was the thermionic emission, that is over the barrier transport, and other was the tunneling transport. Okay, tunneling mechanism. We said let's not concentrate on the other transport mechanisms, and what we found out that the tunneling mechanism or the tunneling current is enhanced when the doping concentration is increased near the junction. Okay, when there is an enhancement in the doping, there will be the thinning of the barrier that carriers need to tunnel. So as a result of that thing, we will be having enhancement in the tunneling current. And also we found out that this thermionic emission, it depends on the barrier height. Okay, so it is independent of the, you can say, it is independent of the band bending inside the this semiconductor side near the metal semiconductor junction. So then we looked into this one-sided P plus N junction, and we saw that how the junction, or the how the region having the high doping will have less depletion width, and the region which is having the low doping will have more depletion width as compared to the highly doped side. So from that we found out, since there is the there are two charges, one on the P side and one on the N side, these immobile ions, they kind of help us to build the concept associated with the capacitances. Okay, and under this under this reverse bias, we said that this capacitance is predominant at the end. This junction capacitance is also bias dependent, and the bias dependency we found out implicitly in terms of the phi bi, which is the built-in potential. Okay, and we said that this Cj is simply given by the expression of 2 times epsilon naught epsilon r, and built-in potential times the reverse bias, and this has been multiplied by the 1 over Na plus Nd. Okay, this was a depletion width which we found out solving the Poisson's equation in the lectures taught by the professor. Okay, so from that we said, since this is an P plus N junction, the accepted doping will be much greater, so we will be able to make an approximation, and we found out from this approximation that the value of the WD can be found out. We put the value of that WD back into the Cj expression, which is the junction capacitance per unit area. Let's be specific, this was the per unit area, and we found out this to be equal to epsilon naught epsilon r times divided by WD. So if when we squared on the both sides, we got this 1 by Cj square as a linear function of the applied reverse bias. Okay, so the slope was the 2 by epsilon naught epsilon r times q and d, and the intercept we found out by saying that by looking into the graph and saying that 1 by Cj square will be 0 at some reverse bias, and that reverse bias is given by the value of 0.75 volts. And we found out the from the slope we found out the value of the donor impurities, and then we found out the built-in potential. From the built-in potential we found out the value of the okay, this Na, the acceptor atoms, concentration of the acceptor atoms. And then we looked into this model, this small signal model of this diode, and we found out uh, the magnitude of that small signal current which was associated with the circuit we were given, which was having the PN junction and the some resistor also associated with it. Then we looked into this junction where we were having donor impurity on both sides. However, on one side we were having high concentration and we were having less concentration on the other side, and as a result of that thing we will be having the concentration gradient, and as a result of that thing we will be having the region, depletion region built between the two sides. Okay, so as a result of this thing, what we got is the conduction band edge on the one side and the conduction band on the other side. The difference between the two will give us the built-in potential, and we looked into the values and found out to be equal to some number which was 60 millivolts. Then we looked into another problem where we solved for this intrinsic region. So we basically had the donor impurities and the acceptor impurities. That is, we had on left side we had the n-type doping, in the middle we had intrinsic region which was devoid of any kind of a doping, and on the right hand side we had this acceptor doping which was p-type. So this in this region, in the intrinsic region, we had zero charge, so the electric field inside that region was constant. So that's what we drew. Okay, and we use the energy balance to find out the phi bi value, and after looking into the phi bi value, we also looked into the electric field which was the maximum electric field that we were told to find, and the depletion width on the n and p side, since on both the sides n and p they were having symmetric doping. So as a result of that thing, we had the symmetric depletion widths. Okay, so we found out the value of the W, we found out the value of the this electric field maximum, and then we moved to the another problem where we had this PN junction in the reverse bias, and we know that this will act as a capacitor, and we placed some inductance in parallel with that PN junction, so as to have some frequency, so as to have this LC tank circuit, and we were asked to find the resonant frequency. Okay, so we found out the resonant frequency, and after that we are told to find the reverse saturation current in an ideal PN junction, and then we looked how much amount of voltage we need to change in order to have a increment of the factor of 10 for this PN junction diode current in the forward bias. So I guess that's it from my side for today's lecture, since all the problems associated with the assignment are done. So we can safely say that we have covered all the PN junction assignment problems. Now, I guess we are having no queries, and because there is no one present over here now, so we can clearly say that uh, we can clearly end this session now, because now if you feel that you have any question, you are always welcome to email. Okay, so since I had been told to solve some of the problems which are associated with the assignments, and I have done those problems, so I request you to look into those problems itself. I have covered them in today's session, so even if you were not able to join, you can easily look into the problems that I solved, okay, today itself. So let us end the session.